Kagglers. I'm going to quickly tweet out that we've started while I wait for the ceremonial lag to catch up. Always takes a tiny little bit. Reading group. Starting now, and then I gotta post a link to the video. And it looks like the stream still hasn't caught up. Okay, Twitch is good, and YouTube. When will YouTube go? But while I'm waiting for that, I can tell you guys what paper we're gonna read. And I was genuinely surprised this week. So you may know we do the voting for papers in two places, so I tweet about it. And you can see here that your options were EfficientNet, which is a more efficient way to train CNNs, Albert, which is a version of BERT that is much smaller than the original BERT model. So these are both sort of like more efficient, smaller model sort of space. And then this other paper, Deep Learning for Symbolic Mathematics, which was actually, I want to say Walter, who you may know as Inversion on Kaggle, was the one who first clued me into this paper. Let me double check, because it might have been somebody else. And I don't want to give credit to the wrong person. And on Twitter, which I think is a little bit NLP heavy because my background's in NLP, and I think a lot of the people who follow me also are in NLP. Albert was, not a runaway winner, but definitely came in first. Jeff Mosier, Jeff last name, one of the Kaggle engineers, is the one who clued me into this deep learning for math paper. But I also do the reading group voting on the Kaggle community page. And as you can see here, the runaway winner was deep learning for math. And this paper is there's actually a question about this on the forums a while ago, is using a deep learning approach to compute symbolic mathematics, which is not something that I would think of as an especially good application of deep learning, but apparently they did it. And I would, excuse me, I'm a little sniffy this morning, I don't know why. And I would like to mention that this paper and also the Albert paper are actually still under review. So they are anonymous, we don't know who the authors are. I'm certainly not going to go checking to see if I can figure it out to try and make anonymity, because that's no good. And hello to everyone who said hi, Abhishek, Javi, Sky, and Leonardo. Sorry, Leonardo, people were not into Albert, because I think that's, Leonardo was the one who recommended Albert. Excuse me, or asked me to include it in voting. Ugh. It's getting to be fall, and I think somewhere out there's something I'm allergic to. Anyway, so in a surprise victory, the winner with 290 votes was Deep Learning for Symbolic Math. The runner-up was Albert with 165 votes, and then poor EfficientNet with 154 votes. I keep putting it in there. I know it's an important paper. People just don't vote for it. So maybe one day we'll read EfficientNet. Javi, or I guess Javi maybe, says, one Kaggle Spanish, please. That would be great, but I don't speak Spanish. But if someone wants to live stream about Kaggle in Spanish, please knock yourselves out. I would love to see that. So, the paper that we're reading, for those of you who are just tuning in, and those of you who are watching the recording, it'll be in the title, I'll change the title, so it won't be a surprise for you, is Deep Learning for Symbolic Mathematics. Now, before we get started, I'm gonna warn you guys, it's been like 10 years since I had any calculus, and I kind of haven't used it in the interim. I've really only done much with a lot of statistics stuff, of course, and then mostly linear algebra. I guess like a little bit when I was learning the chain rule, like a tiny bit. So I'm gonna need some help, probably. But I think it's a really interesting application. So let's get started on this paper that I should say is under review. We don't know who the authors are. We don't know who's going to be reviewing it. So this is just sort of us testing the waters. Hubby says, deep learning is so cool, duh. And someone's like, did you catch a cold? I hope not, because I just donated blood. I think it's allergies. We'll see. Sky said I voted for a fish and that. I know. One day. Maybe I'll just make an executive decision and we'll read that one next. All right. And Javi says, I can help. Yes! Live stream in Spanish, please. I'd love to see more content in other languages. All right. We don't know who the authors are. It's submitted to ICLR, so the International Conference on Learning Research, I guess? I definitely said that it was at ICML, which I do not think is the correct thing. Learning Representations, there we go, which is different from ICML, which is the International Conference on Machine Learning. Oh, it's going to be in Ethiopia. That's cool. There was just a big deep learning conference in Ethiopia last week, a couple weeks ago. So this is submitted to ICLR. Abstract. Neural networks have a reputation for being better at solving statistical or approximate problems than at performing calculations or working with symbolic data. That's true. I probably wouldn't use a neural network for working with symbolic data. In this paper, we show that they can be surprisingly good at more elaborated tasks in mathematics, such as symbolic integration and solving differential equations. We propose a syntax for representing these mathematical problems and methods for generating large data sets that can be used to train sequence-to-sequence models. We achieve results that outperform commercial computer algebra systems such as MATLAB or Mathematica. Okay, interesting. Excuse me. Baghdad says, how long will it take? Probably a couple hours, especially because I'm not going to read this one super fast. All right, introduction. I'm going to zoom in a little bit so you guys can see a little bit better. A long-standing tradition in machine learning opposes rule-based inference to statistical learning. Rumelhart et al. 1986 is what those say. And neural networks clearly stand on the statistical side. So this is the rule-based stuff, at least in NLP, was more around things like expert systems that were really big in the 70s and 80s, I want to say, and into the 90s. And then statistical learning, which are things like, deep learning or a lot of more modern machine learning methods tend to be more on the side of statistical learning than rule-based learning. Cyanide says, I'm not able to see the chat. Can anyone help me? So I'm paying attention to you both, but there is a chat on Twitch and there's a chat on Kaggle's YouTube. So here, I can post the YouTube link for you. There you go. So the topic is, again, deep learning for symbolic mathematics. So neural networks clearly stand on the statistical side. They've proven to be extremely effective in statistical pattern recognition and now achieve state-of-the-art performance in a wide range of problems in computer vision, speech recognition, natural language processing, etc. However, the success of neural networks in symbolic computation is still extremely limited. Combining symbolic reasoning with continuous representations is now one of the challenges of machine learning. So this sort of relates to the paper we read a while ago, you'll remember, where they were looking at inference in, what was the corpus? Anyway, there was sort of like the paper where there's the warrant, and then there was the statement, and then sort of the thing that you needed to know to justify the statement, and then they needed to figure out which of the two statements actually supported the statement, if you guys remember that. So that would be inference in a natural language processing setting. Only a few studies investigated the capacity of neural networks with mathematical objects, and apart from some few exceptions, Zarembra et al. 2014, Luce et al. 2017, Alamanis et al. 2017, the majority of these works focused on arithmetic tasks like integer addition and multiplication, etc., etc., etc. And I want to say like a couple years ago, we read the chapter from Speech and Language Processing that talked about neural networks and why you have to have a deep neural network. And it's because otherwise you can't do things like multiplication. Frank says, dumb question. How does it outperform Mathematica? Mathematica should always give the right answer, provided it knows how. Good question. I don't know. Presumably they're going to talk about it. Also, like, MATLAB is like a language? I suppose they mean the applicable methods in MATLAB. I'm hoping that they'll tell us. I assume this paper has multiple authors because most machine learning papers do, but I could be wrong about it. It could be one person. I guess you could also say they for one person, so it's right either way. On these tasks, neural approaches tend to perform poorly and require the introduction of components biased towards the task at hand. So the way they're saying, like, if you want to build a calculator that does addition and multiplication, why would you use a neural network? It doesn't work very well. In this paper, we consider mathematics and particularly symbolic calculations as a target for NLP models. Okay. More precisely, we use sequence-to-sequence models on two problems of symbolic mathematics: function integration and differential equations. So sequence-to-sequence models are things that you would use for, like, machine translation, where you have an input sequence and then the output sequence would be in a different language. This is surprisingly NLP. I'm feeling better about this paper already. Yeah. Sharam says, responding to Frank, I think they might mean detection of equations, so finding that there is an equation. And they might perform in another metric, like it might be faster. I don't know. We'll see. We'll see. Both are difficult, even for trained humans. Sure hope they don't ask us to do this in the course of reading this paper. Humans typically learn a set of rules, techniques, and tricks, integration by parts, change of variable, etc., that are not guaranteed to succeed, while computer algebra systems solve equation using complex algorithms. Geddes et al. 1992. So this is presumably what they're evaluating against. For instance, the complete description of the Reich algorithm for function integration is composed of more than 100 pages. So that must be the algorithmic description, like you'd have in a computer science paper, and not like the code, I'm guessing. This feels very mathy, which is, I haven't read a whole bunch of math papers. Pure math. Yeah. Yet, function integration is actually an example where pattern recognition should be useful, detecting that an expression of the form 2y prime y squared plus 1 to the negative 1/2 suggests that its primitive will contain the square root of y squared plus 1. Sure. Ooh, that feels like something I would have been able to figure out at some point, but it's rusty right now. Detecting this pattern may be easy for small expressions y, but may become more difficult as the number of operators in y increases. However, to the best of our knowledge, no study has investigated the ability of neural networks to detect patterns in mathematical expressions. Okay. We first propose a representation of mathematical expressions and problems that can be used by sequence-to-sequence models, and discuss the size and structure of the resulting problem space. Then, we show how to generate datasets for supervised learning of integration and first and second order differential equations. Finally, we apply transformer networks to these datasets. So transformers read this paper, that's the Vaswani et al. 2017 paper, and BERT is also the first half of a transformer network. So transformer networks are... The original sort of vanilla transformer has an encoder and a decoder, and it uses attention, where attention is distributed over the entire input sequence. So instead of something like a recurrent neural network, where you're looking at the previous, your network is looking at the previous items in the string, and then you sort of move forward and then look back and move forward and look back and move forward and look back. A transformer network looks at everything on the first pass, using sort of like stacked modules. And the benefit of that is that you don't have to have that training time bottleneck where you have to wait for the network to finish before you can move on. So they're faster to train in that way. And again, vanilla transformers are used for sequence to sequence, so they've done pretty okay in machine translation, and BERT and other transformer-based language models are taking the first half. So there's an encoder that takes the words in and gives you numbers out, and then a decoder that takes the numbers out and then produces words out, basically, is the NLP version. And so here they're going to have, maybe they're going to talk about this, so they're probably going to have an encoder that takes in the mathematical notation and produces this sort of feature space representation, and then a decoder that takes the feature space representation and gives you the solved equation, I'm guessing. We'll see. I'm just hypothesizing here. Yeah. And if you want the link to the paper in the voting for the paper in the YouTube video description, you should find the link to the community post that has the link to all the papers that we voted on. All right. And then they apply transformer networks and achieve better performance in state-of-the-art computer algebra programs, namely MATLAB and Mathematica. I have not used MATLAB or Mathematica to like solve equations, so I'm not entirely sure what they mean by that. Oh, let me get these out. We don't need those. Cushy says, hello, how's it going? It's going pretty good. We're getting into this paper. All right. Mathematics is a natural language. It's not. Expressions as trees. Mathematical expressions can be represented as trees, with operators and functions as internal nodes, operands as children, and numbers, constants, and variables as leaves. The following tree represents expressions 2 plus 3 times 5 plus 2, 3x squared plus the cosine of 2x minus 1, and don't know what these are called. Theta squared trident? Is that a psi maybe? Maybe that's a psi divided by theta x squared minus 1 over slanty v squared. Oh gosh. This whole guy. This is why I'm doing it as a video, so I can just be like, these guys. So the idea is that you can take this structure and create a tree diagram from it. So using our old friend PEMDAS, the first thing you would evaluate would be the thing in parentheses. So here we have this this number. So the leaves, the terminal nodes. People are saying partial derivatives. Laughing face, laughing face. Frank says, I don't think MATLAB is quite a computer algebra system, is it? Usually you use it for matrix computations, not symbolic differential equations. And people are like, it's a partial derivative, Rachel. Thank you. I told y'all, it's been 10 years. I haven't used it in the interim. Yer says, second derivative, partial derivatives, calculus. Yes, I'm just going to say this fits calculus. But the idea is that you have the... it looks like it's necessarily a binary tree. So the nodes are the numerics and the numbers and the variables and the constants that you're putting into the equation. So phi. Alan is saying this is phi. So phi is a constant, it must be, or maybe a variable. And it's an input into this equation. I'm having a hard time saying this with words. Kushi says, I am Greek, it's your lucky day. Thank you. Psi. Psi is this one, PSI. So from the simplest case, we have our constants on the edge, and then when two constants, when two inputs are transformed by some, operator or function, then that node is created linking those two, and then the output of that, so 5 plus 2, is passed as the input along with another constant to another node, so 3 times 5 plus 2, and then the output of that is passed as the input into this head node, and then if you ran through and did all of these equations in this order of operations, you would have a output, which in this case is 23. 5 plus 2, So 7 times 3 plus 2. So 21 plus 2, 23. Yeah? Yeah? Arithmetic, never my strong suit. So the idea is that you can break down even a very large equation into a number of binary operations where the input to each operation is either the output of a previous operation or a input to the equation, so like a constant or a variable or a number. Okay, that makes sense. I think that's a fairly intuitive way of representing equations, but also I've had a lot of formal syntax training, so that might be that. People are saying, Subham says, yes, it has to be a binary tree. Saram says, Rachel, don't we see partial derivatives in backpropagation in RNNs? Yes, that's the only time I've looked at calculus even a little bit. And often I think it's fairly common for people to teach backprop without using the calculus and just using the chain rule instead. Sorry, no, the chain rule is the calculus. Like, it's a calculus operation, but oftentimes people will explain it in other ways that don't rely on calculus background. And psi is a function of time in this context. Thank you. So you have this function. Interesting. Okay. Helpful. And someone else said it looks like a parse tree or an abstract syntax tree for a computer language. And yes, I would agree. And Kushi is saying it's not I, like C. So this one is C. Thank you. Trees disambiguate the order of operations, take care of precedence and associativity, and eliminate the need for parentheses, and are also extremely space inefficient, which is why people don't generally use them, unless they're writing syntax papers. Up to the addition of meaningless symbols like spaces, punctuation, or redundant parentheses, different expressions result in different trees. With few assumptions, discussed in Section A of the appendix, there is a one-to-one mapping between expressions and trees. Okay, that makes sense to me, because if we changed anything in this expression, like if we made this to be 4 instead of 2, we'd have to change it in our tree as well. If we change this to subtraction instead of addition, we'd have to use that in our tree as well. So there should be there's no possible ambiguity in the tree structure, and the tree structure will only map to one potential expression, which is, and I should say this, very different from natural language. In natural language, given a sentence, there are sometimes many multiple valid tree structures that could be derived from that sentence. So again, it's not natural language. All right. So the first thing that they're doing is they're taking equations and they're creating abstract syntax trees from them. If you have a computer science background, or parse trees from them if you have an NLP background, or it's not really a decision tree, a tree structure from it. Ear says, it's a kind of notation that TensorFlow used to make its operation class to apply autodiff, to apply lighter gradients. And Suvam, each node need not necessarily have 2 children. Maybe they'll talk about that? I guess if you had, so functions are internal nodes. So you're saying in a situation where a function had multiple inputs at the same time, you could have a tertiary tree? Well, presumably they'll talk about it if it's a necessary restraint. Alan says, interesting, but 2 different trees could give the same solution if you switch the organization of the expression. Yes, you could get the same output from 2 different trees. And people are talking about where they learned convolution. Leonardo says, you study convolution transformation in calculus courses, and it's the reason why CNNs work. Have not worked with CNNs a whole bunch. And then Viraj says, I really learned convolutions in digital signal processing. Makes sense. All right. We consider expressions from a syntactical perspective as meaningless sequences of mathematical symbols. Okay, 2 plus 3 and 3 plus 2 are different expressions, as are the square root of 4x and 2x. They will be represented by different trees. Okay, so you can't transpose order, and order is important in the trees. X divided by 0, the square root of -2, or the log of 0 are also legitimate expressions, even though they do not necessarily make mathematical sense. In practice, expressions represent meaningful mathematical objects. Since there is a one-to-one correspondence between trees and expressions, equality between expressions will be reflected over their associated trees as an equivalence. Since 2 plus 3 equals 5 equals 7 minus 12 equals 1 times 5, the 4 trees corresponding to these expressions are equivalent. So the structure won't be the same, but the output will be. For instance, expression simplification, a standard problem in formal mathematics, amounts to finding shorter equivalent representation of a tree. In this paper, we consider 2 problems, symbolic integration and differential equations. Both these problems boil down to transforming an expression into another, e.g. mapping of a tree of an equation to the tree of a solution that satisfies it. We regard this as a particular instance of machine translation. Sivam says they claim one-to-one mapping between the expression and the tree, not the solution. Yeah, so actually having multiple trees per solution is necessary for the rest of this paper, I'm guessing, because what they're doing is they're trying to find a simpler tree that has the same output. Sram says 2 different trees could give it if the switch happens at commutative binary operations. Yeah, also, sorry, I'm just thinking about the switch here, but I guess if order matters, like the order of the leaves, as you read down the tree, then I guess those are different. All right, trees as sequences. Machine translation systems typically operate on sequences. Yes, that's true in the language is sequential. Alternative approaches have been proposed to generate trees, such as tree LSTM or recurrent neural network grammars. Dreyer et al. 2016 and Iraguchi et al. 2017. However, tree-to-tree models are more involved and much slower than their sequence-to-sequence counterparts. That's putting it lightly. Both at training and inference. Also, you need to, in order to have a model that constructs trees, you need to make some strong assumptions about what those trees are going to look like. For example, if you are parsing natural language, you have to pick a model. So you have to pick like head-driven phrase structure grammar or HPSG or like the Penn tree bank tree structure. Like you have to make a lot of decisions about what those trees are going to look like. For sake of simplicity, we use sequence-to-sequence models, which were shown to be effective at generating trees, e.g. in the context of constituency parsing, Vignals et al. 2015, where the task is to predict a syntactic parse tree of input sequences. So they're suggesting that they're going to use sequence-to-sequence models because sequence-to-sequence models can be used to generate trees instead of doing all of the tree structure themselves. Kushi says, are you doing a doctorate? I have a doctorate in NLP. Interesting. Saram says, I'm loving this paper. Oh, good. I'm glad that people voted for it then. Leonardo says, looks interesting. Since 2 trees could have the same output, you could just switch to the more simple tree. Yes, I think that's the idea they have. And Leonardo says, and the other way around. So you could take a very simple equation and make it just awful for, I don't know, trolling reasons. Or I guess if you wanted to generate problem sets, if you were a math professor, you could do it this way. Using sequence-to-sequence models to generate trees requires to map trees to sequences. Yes, that makes sense, unless you are starting with a sequence that you already think has an underlying tree structure, as natural language does. To this effect, we use the prefix notation known as normal Polish notation, writing each node before its children listed from left to right. For instance, the arithmetic expression 2 plus 3 times 5 plus 2 is represented as the sequence plus 2 times 3 plus 5, 2. So here we're writing basically this tree. So if we're writing it top to bottom, would be plus 5 times 3 plus 5, 2. Plus 2 times 3? Plus 5, 2? Plus 5, 2. Yeah, okay, it is the same. Excellent. So this is the top node. This is a child of the top node. This is the left child of the top node. This is the right child of the top node. This is the right child of this node. This is the left child of this node. This is the right child of this node. This is the left child of this node. Does Polish notation work for non-binary trees? I should say, in linguistics, non-binary trees are, all trees are binary, pretty much. In contrast to the common infix notation, 2 plus 3 times 5 plus 2, prefix sequences need no parentheses and are therefore shorter. Inside sequences, operators, functions, or variables are represented by specific tokens, and integers by sequences of digits preceded by a sign. As in the case between expressions and trees, there exists a one-to-one mapping between trees and prefix sequences. Ryan says, I suggested we read tree LSTM a while ago. Interesting it's still popping up in current papers. Yeah, I haven't seen it in any NLP papers that I've read recently, but it does seem to be having broader adoption. Leonardo says, no, since we are talking about symbolic math, some representations are more pleasant than others. It depends on the context. Okay, helpful, thank you. I'm assuming that's about whether or not, whether you can use Polish notation for non-binary trees. All right, generating random expressions. In this work, we want to generate a training set of mathematical expressions. However, sampling uniformly expressions with n internal nodes is not a simple task. Naive algorithms, such as recursive methods or techniques using fixed probabilities for nodes to be leaves, unary, or binary, tend to favor deep over broad trees or left-leaning over right-leaning trees. Here are examples of different trees we want to generate with the same probability. So you can see that this one is very right-leaning, I guess, because it's always, all of the nodes are always generated off the, right-leaning, because all of the nodes are generated off the right side. This one is left-leaning, all of the nodes are generated off the left side. This one is sort of a balanced tree. Yes, that is a balanced tree, so it's sort of going down and out equally, and this one is sort of going down further down here. And you can see here that these are not, this is not a binary tree. It has some unary operations. Just like X-bar, for those of you who have had syntax in like the early 2000s. Sorry. So what they're saying is that they can't just create like a recursive method that generates trees, because they're going to get like all their trees will look like this, or all their trees will look like this, and you're not going to get a wide variety of different tree structures. Yeah, and Saram says, even in non-binary trees, I think the order of the nodes will resolve any disambiguity. Disambiguity? I don't know where the stress is there. And Akash says, so it's kind of like doing postfix expression evaluation done using stacks. I know some of those words, maybe. Maybe someone who's more familiar can confirm that for Akash. In section B of this appendix, we present an algorithm to generate random trees and expressions representative of the whole problem space, and where the 4 expression trees above are all generated with the same probability. In the next section, we investigate the number of such possible expressions. So they've got a big, probability space of possible expressions. They want to sample evenly from it, and that's in the appendix, just like in section A, where we have the discussion of the proof that each expression can map to exactly one tree. All right, counting expressions. Expressions are built from a list of operators, variables, i.e. literals, and integers sampled over a finite set. Based on the task of interest, more involved operators can be used, like differentiation or integration, etc. Calculus. More precisely, we define our problem space as trees with up to n internal nodes, a set of P1 unary operators, e.g. cosine, sine, exponent, and log. So here's a square root, which is a unary operator. A set of P2 binary operators, plus, minus, times, to the power of. And a set of L leaf values containing variables, e.g. XYZ, constants, e.g. E and pi, Euler's constant, I think? Integers, or is that the natural log? I think that's natural log. Integers, e.g. negative 10, blah, 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 to positive 10. So you could define a problem space with a tertiary or n-ary tree, but they only have up to binary branches at each tree. Up to a binary operation at each node, and also unary ones. Cushy says it's pronounced P, not pi, XD. This one? No, people definitely say this one pi. Now you're trying to trip me up. All right. If P1 equals 0, expressions are represented by binary trees. Okay, so if you don't have any unary expressions, then all your expressions are binary because all of your other operators are binary. That makes sense. The number of binary trees with n internal nodes is given by the nth Catalan numbers CN, Sloan, 1996. Don't know what a Catalan number is. A binary tree with n internal nodes has exactly n plus 1 leaves. Each node and leaf can take respectively P2 and L different values. So each node can take P2 values if you don't have any unary operators, and your leaves L can take L different values based on the set of possible values you defined previously. As a result, the number of expressions with n binary operators can be written as expressions n equals Cn, still don't know what Catalan numbers are, P n2 L n plus 1, so approximately, or is proportional to, that's approximately, 4n divided by n times the square root of pi times n, and that expression times P2, so the number of binary operators to the nth power, and the number of leaf values to the nth power plus 1. So a lot. Saram says, oh my god, Catalan numbers revisited. Nightmares for a math major like me. All right, I'm not going to look those up. I leave that as an exercise to the reader in the best tradition of math papers. Kushi says, I swear in Greek it's P, so this one pi. I really view, but I'm going to say it pi because I think that's more familiar to me. I'm going to keep doing what I was taught to do. All right. If P1 is greater than 0, the number of trees with n internal nodes, so if you can also have unary operators, the number of trees with n internal nodes is the nth large Schrödinger number, that's not Schrödinger, SN, Sloan 1996. It can be computed by recurrence using the following sequence. N plus 1 Schrödinger number equals 3 times n2 minus 1, Schroeder to the n minus 1 minus n minus 2. Schroeder n minus 2. I don't know what that one is either. Again, big, I'm assuming. Finally, the number E of expressions with n internal nodes, P1 unary operators, P2 operators, binary operators, and L leaves is recursively computed as n plus 1 En, where E is the number of expressions, equals P1, so the number of unary operators, times 2 times the number of leaves times the number of binary operators, times 2 times the number of, what is n? The number of internal nodes you specified, minus 1 times en minus 1 minus P1 unary operators n minus 2 en minus 2. I'm just gonna assume that this is right. If any of you want to try to rederive that and check it, feel free. I'm not going to. Leonardo is asking Sram to describe Catalan numbers. What am I drinking? Water. I gotta stay hydrated. And I use a straw, so I think it's less gulpy sounding on the mic, but especially when I'm talking, gotta stay hydrated in the throat. Akash says, Catalan numbers are like natural numbers, which may end up repeating an accounting problem, so hence making them be defined using a recursive loop. Okay. Alan says, it's Greek letter P, but pronounced pi. Did I pay no attention in my math class? I'm pretty sure this is pi. Don't tell me this one isn't pi. Like, I remember this very distinctly from math. I don't necessarily remember all of the calculus, but I remember that one's called pi. And Saram says about Catalan numbers, Akash is right. Adding on to that, the closed form expressions of Catalan numbers appear in a variety of counting problems, like how normal permutation and combination expressions appear. Okay, helpful. Counting sounds like one of those places in math, like number theory, that you think you could get, and then you start looking into it and you're like, oh no, abort. Not that you should abort, but you would probably benefit from guidance in that way. I only really learn math effectively from lectures, personally. Anyway, that's just me. All right, 3, generating data sets. So here we have a formal description of our decision space, or the formal description of the number of possible trees that we could have given these constraints that we have chosen. All right, generating data sets. To train networks on mathematical subjects, we generate data sets of problems and their solutions. Also, I would just like to say, this is very mathy. I would probably just have scraped things from math papers, is what my solution would have been here instead of generating the data, but that's me. Ideally, we would like data sets to be representative of the problem space. Actually, I'm just realizing that the reason that I say that is because generating natural language data for training NLP problems can go real squirrely. Like, it can get real weird, so we generally prefer to use natural language data. I generally prefer to use natural language data. Sorry for the aside. Unfortunately, some functions do not have an integral which can be expressed with usual functions, e.g. f of x equals exponent of x squared, or f of x is the log of x. And solutions to arbitrary differential equations cannot always be expressed with usual functions. To address this issue, we propose other approaches to generate large training sets for integration and first and second order differential equations. So they're saying because they're working specifically with integrals, they sometimes get funky looking stuff, so they can't generate it using their generation algorithm they just spent a page explaining. Integration. For integration, we generate random functions with up to n operators using methods from section 2. So this is for choosing the number of operators, not for the number of inputs to each operation. and calculate their derivative with a computer algebra system. The derivative becomes the problem, and the original sample the solution. In that setting, we simply train the model to predict the generated function given its derivative. Okay, so what they did was they solved the equation using, they generated some equations, and then they solved them, and then they used those as a training set. Helpful. Ryan says, joke. Definitely pie, but pronounced poo rhymes with moo. Okay. Okay, so that's how they're generating their training data. So they do still need their tree generation. It's not tree, their equation generation using their tree model in order to get the things that they then get the derivative of. So they are generating their data, and then they're solving the equations, and then that's what they're using as their training data. So this would be similar to in a NLP setting, doing like that thing where you run your text through machine translation and then back again to augment your data. If you were building a machine translation system, which is actually kind of common. The Stig says they want to train an integration model, but the derivatives can already be easily done. I think their argument is that their model is going to, it's been done using Mathematica or MATLAB, they don't say which one, and then earlier in the paper they suggested that their model could outperform Mathematica or MATLAB, which I'm guessing, is going to be that it's faster, is my guess, because if it always gets the right answer, which hopefully it would, then it must be, the performance issue must be a difference of time. I don't know, they haven't talked about it too much, but yeah. Alan says, could someone explain to me why you generate the solution of the problem you want to solve? Then what is left to solve? I have found a hard time understanding this. That's a great question. So the reason that they're doing this is because sequence-to-sequence learning is a supervised problem. So you have an input sequence and an output sequence, and you know that they map to each other. So in order to train their deep learning model, they need to have examples of good input and output sequence pairs so that their model can see those patterns and generate statistical generations from them. So like for a machine translation problem, to train a machine translation model, let's say from Swahili to Russian, you would want examples of the same text in Swahili and Russian so that you can go back and forth between the two and check your model. That's the reason why you would want to. That's the reason why you have to solve the problem before you can solve the problem. Deep learning models can't deduce problems there from first principles. They need to see a lot of examples, and the more examples, the better. Yeah. Alan says, if you can solve a problem, then it is simple enough. What happens when you're out of samples of hard problems? That's a good question. I mean, if it's genuinely hard to do, also it's going to be really hard for a deep learning system to do, and if you want a deep learning system to do the hard thing, you're going to need much more training data. Generally, the more complex the task, the more training data you need, in general. Yeah, and Saram's like, yeah, you were right. And the Stig says, so one way is to do it the easy way and then reverse hard problems. Yeah. All right. First order differential equation. All right. We now present a method to generate first order differential equations with their solutions. We start from a bivariate function, f of x and x, such that the equation f of x and y is c, where c is a constant, equals c, where c is a constant, can be analytically solved in y. In other words, there exists a bivariate function f that satisfies, for all of x and c, f of x is little function, second f, of x times x and c equals c. So if you're trying to solve for y, you should be able to do it given only x and c, where c is some constant. By differentiation with respect to x, we have that all of x and c... I'm just not gonna read that, sorry guys. Something derivative, something. Questions? Leonardo says, this is symbolic math. They are more concerned with representations of the equations and expressions, not the results or outcomes. And Rahul said, since they are generating solutions since MATLAB or Mathematica, their model will be as good as MATLAB or Mathematica, presumably. Akash says, won't the generated data be a higher order as if you provide a derivative to the model, then the data predicted cannot be just first order integral, but any. Multi-ordered as any higher order integral of the same function will give the same derivative, though order may vary. Maybe? It's been a really long time. I don't remember very much from calculus, so maybe. If someone else knows, please feel free to hop into the chat. And Alan says, thank you, Rachel. This has actually helped me know how I can use ML to solve optimization models. Good, I'm glad. Saram says, I think they're actually interested in solving just representations. And Saram says, Rachel, this is the standard trick in math. Okay, thank you. And the Stig says, so they're creating an integral solver, but not because this type of integral solver doesn't exist yet, but because they think theirs will be faster. Is this something where computing power is the limiting factor? I think the main thing about this paper is they're just showing that you can do it with neural networks, because previous work on symbolic math using neural networks has been not super promising. I think they mentioned some papers where like addition and subtraction using neural networks didn't work super great. So they're proposing a new approach to allow you to work on the problem. Is the thing that they're proposing here. So yeah, I think that's the general idea of why they're writing this paper. And also this the conference is a machine learning conference, so the applications are sort of less important than theoretical advancements in the field of machine learning. Would I have spent my time on this? No. But I guess if you're working in symbolic representations, this is a very interesting problem to you. Saram says the original equation is f given x and c equals y, but it is harder to solve these. Instead, we look at functions that take only constant values. Yes, I think that's what they said. Audio is kind of low. Woo-woo-woo. How's that? Let me know if I start sounding a little bit peaky, but that should be a little bit higher. All right. As a result of any constant c, fc is a solution of the first order differential equations. I'm going to take their word for that one. With this approach, we can use the method described in section C of the appendix to generate arbitrary functions f of x and y analytically solvable in y, and create a data set of differential equations with their solution. Wow, these appendices are doing a lot of heavy lifting. Alternatively, instead of generating a random function f, we propose to directly generate a function f of x and c solution of a differential equation that has to be determined. Okay, so you generate a function solution, and then you have to figure out which equation the function is a solution to. If f of x and c is solvable in C, we can simply compute the function f that satisfies f of x and c equals c. By applying the approach above, we have that for any constant cx, arrow with a foot, f of x and c is solution of the differential equation 3. Finally, the resulting differential equation is factorized, and we remove all positive factors from the equation. Okay, and people are saying the audio is good for them. Helpful. So Ram says, original equation is f of x and c equals, I already read that. And then the Stig says, I guess I would have figured maybe integration is a harder problem to solve than derivatives, like how it's much easier to multiply two large primes than to find those two primes with only the final answer. Maybe I don't have good intuitions about that. Again, it's been a minute, and there's a light splotch on the green screen, so it looks kind of green. I thought I'd fixed all of those. Anyway. All right, a necessary condition for this approach to work is the solvability of C of generated functions f of x of x and c. For example, the function f of x and c equals c times the log of x plus c cannot be analytically solved in C, i.e., the function f that satisfies f of x and c equals c cannot be written with usual functions. Since all the operators and functions we use are invertible, a simple condition to ensure the solvability in C is to guarantee that C only appears once in the leaves of the tree. That C only appears once in the leaves of the tree representation of f of x and c. Okay, I see what they're saying. So because C shows up twice here, there are multiple possible solutions that C could be. So in order to get around that, they're going to make sure that C only shows up once. A straightforward way to generate a suitable f of x and c is to sample a random function f of x. Sorry. You can definitely find it multiple. You can definitely solve for C if it shows up multiple times. It must be something about the log and the multiplication that makes it unsolvable. Again, I'm just gonna take their word for it. This is pretty out of my wheelhouse. A straightforward way to generate a suitable f of x and c is to sample a random function f of x by the methods described in section C of the appendix, and to replace one of the leaves in its tree representation by c, where c is a constant. For instance, we've generated a random function f of x equals x times the log of c divided by x. We solve in C, we differentiate in x, and then we simplify. So here, I see. So here they've generated their random function, and then they've replaced one of the leaves in C. That makes sense. So Ram says, arrow with a foot. This guy means is definitively mapped to. Thank you. Helpful. Okay, so that seems like a pretty reasonable way of generating these trees given the constraints in order, the constraints that they've talked about. All right. So I think we could get through this bit, especially because I'm not going to read these equations out loud. Our method for generating first-order equations can be extended to the second order by considering functions of three variables, f of x, c1, c2, that can be solved in C2. As before, we derive a function of the variables such that f of x, c1, c2, c1 equals c2. Differentiation with respect to x yields a first-order differential equation, as shown in the text, where f of c1, c2 equals x is definitively mapped to, thank you, Saram, f of x, c1, c2. If this equation can be solved in C1, we confer another three-variable function g satisfying for all x that g of x, f of c1, c2, x, f prime c1, c2, x equals c1. Okay, I'm just floundering now, y'all. Okay, sure. You could organize those symbols in any way, and I'd be like, yes, I guess. Differentiating with respect to x a second time yields the following equation. Sure does. Can we get back to the deep learning? Therefore, for any constant c1 and c2, f of c1, c2 is solution of the second order differential equation. Okay. We've got some double primes here. Using this approach, we can create pairs of second-order differential equations and solutions, provided we can generate f of x c1, c2 is solvable in c2, and that the corresponding first-order differential equation is solvable in c1. To ensure the solvability in C2, we can use the same approach as for first-order differential equations, e.g. we create fc1, c2 so that C2 has exactly one leaf in its tree representation. For C1, we employ a simple approach where we simply skip the current equation if we cannot solve it in C1. Although naive, we find that the differentiation equation can be solved in C1 about 50% of the time. Another strategy to ensure the solvability in C1 is to propose in section D of the appendix as an example. Here's the example. Okay, so they start by generating their function here, or they generate it with two. For C1, C2 has exactly one leaf in the representation. Okay, so they use the same general strategy that they do up here, except instead of C having exactly one leaf, they make sure that C2 has exactly one leaf. And then if it can't be solved in C1, they just chuck it. So they're reducing the size of the training data set due to that, but it sounds like they do have a solvable equation about 50% of the time. Strom says, I think they mean if we can't do a variable separable method. Okay. And I am reading the paper Deep Learning for Symbolic Mathematics, and we do it Wednesdays at 9 a.m. Pacific. So I will be back next week as we talk about things like dataset cleaning and the experiments and evaluation. And results. And then the related work right at the end. I hate that. I think you guys know that's not my favorite. I like the related work at the top. All right, well, I would say about a third of this paper is just going directly over my head, but the general idea seems kind of cool. So they're generating equations, they're solving the equations, and then they're using the generated equations and the solved equations as sequences, and they're putting them into a sequence-to-sequence model, specifically a transformer, and hopefully we'll have more details about that transformer soon. And this is in contrast to earlier solutions where they represented equations as trees, like so, and then they were using the parsed trees as the input and output to models, which also requires the parsing, and I think you have to make less decisions about tree structure, and I think trees for equations are simpler than structural syntactic trees for natural language, so it might be a little bit more tractable of a problem, but still very slow. Parsing in general is pretty slow. So, the Stig says, don't miss my ODE class at all. Ordered differential equations. All right. And okay. Yeah, so I'm getting the sort of general idea of what they're doing. I'd have to do probably like a couple weeks of calculus to like get back on to the differentials and differentiation train, because I thought I remembered some of it. I do not. I got off that train a really long time ago. So thank you from 4. Thank you for joining me today. It's about time for me to wrap up because I've got so much other stuff to do today. And we will start with the data set cleaning when we come back next week, so section 3.4, and that will be next Wednesday, 10/9 at 9 a.m. Pacific. And then this Friday, October 4th at 9 a.m. Pacific, I will be doing some live coding. But I didn't do any last week because I was out of town, and I don't know what we're gonna do yet. I'll announce it on Twitter beforehand, so you guys can decide if you want to join or not. All right, thank you for joining me today, everybody. Thank you for telling me what the math words are, because this again is more into the pure math than I think I've ever gone. And we'll pick it back up next Wednesday. I'll see you all on Kaggle. Bye.